Hey Algebra 2, here is your Unit 8 review video. I'm going to go through the whole packet. Just remember that only half of this packet is day 1 and the second half is going to be day 2. You guys in second period, I give you a different packet, so the problems are the same, but I reordered it so that it kind of follows the flow of the actual test you guys are going to take. So if you're looking for a certain problem, just look throughout the packet to find that problem. They'll be the same, okay? There's a couple problems I added in there, and you can add it to your packet or do it on scratch paper. I know sometimes there's you run out of room as you go through it, but just do it on a separate piece of paper, and that should help you out. Okay, so this first one, an exponential function, f of x equals a times b to the x. This can model the data in this table. So what we want to do is create a function that best models this data. So we're going to use this idea that f of x equals a times b to the x. And so basically what we need to find is we need to find a and we need to find b as well. Okay, so let's first start look at a. So I know that when x is 0 that the function is going to be equal to 50. Okay, so let's just write that out. So I know that the function will be equal to 50 when x is 0. So I plugged in that 0 where the x is. Now if we think about it, what is any number raised to the power of 0? Well, it's equal to 1. So let's simplify this. Okay, so the b to the 0 is equal to 1. Well, now a times 1 is just a, and there's our a value. A is equal to 50. Okay, so there's the first piece of our function that we're looking for. So first we have the a, which is 50, but now we still need to find the b. Okay, so to find the b, we're going to use that same idea that, well, I knew that at 0, f of x is 50, but at 1, it's equal to 43. So let's use what we already know. We know that we know that at 43, or if I plug in 1, that it's going to equal 43. So let's make our function equal to 43 and write in 50 because we found that already. And the only variable we're looking for is the b. And I'm going to substitute the 1 for x because I know if I plug in 1 that I should end up with 43. So now the only variable I have to solve for is b. Okay, so now in this next step, well, I know that b to the 1 is just b itself. So now we have 43 equals 50b. And now we're just going to use our usual solving equation skills here. And let's isolate the variable. And we can do that by dividing both sides by 50. 50 cancel out. And then b is equal to 43 over 50. And there's our b. Now understand you guys are not going to have a calculator on the first day. So you wouldn't actually punch this in and figure out what is the decimal value. So you literally just take that 43 over 50, and then we're going to plug it in to where b should go. Okay, so do one step at a time. First find your a, and you can use that. You can use the same steps I just used for the next problem. Figure out what is a when the x is equal to 0. Plug that in. That should give you a, and then use the next value for x is equal to 1. Plug in that 43 and the 1, and that should give you your b. Okay. Okay, so I'm going to kind of go through the next one a little quicker since we're going to use the same steps. So again, we're going to write in another exponential model or function for %p as a function of time. So let's write our model function. Now in the previous one we did a and b and then x as our kind of variable. In this problem our variable is not going to be x, it's just going to be replaced with t. So the same thing, but now we're going to use t instead of x. And actually what we'll do is, since we're talking about a percent, instead of f of x I'll write p of x, just to use the same consistent lettering. Okay, so we'll still have a, we'll still have b, but in this time we'll have t, which is just, again, these values here on the left of our table. So again, let's find the first value. So first I know that when t equals 0, that our function is equal to 100. And we're looking for a. And again, we're plugging in 0 for that independent variable, which is our t. And I know that b raised to the 0 is just equal to 1. So this is a times 1. And simply a is equal to 100. Now some of you guys are going to see this pattern and go straight from the first step to the last step, which is totally fine. I just want you to see how it works out. Okay, but if you want to go straight to the last step, that's totally fine with me. Okay, now we need to find our b. So I know that the second data point, 1 and 112, that 112, or that 1t is equal to 1, our function is equal to 112. So let's plug in 112. Oops, sorry. And we know that our a is 100. And we still haven't found b. So now we're going to plug in 1, because at 1 we get 112. And then b to the 1 is just b. So now let's isolate our variable by dividing by 100 on this side and dividing by 100 on this side. And now b is equal to 112 over 100. And they're both even numbers, so we can simplify those. So let's divide both of them by 2. Well, that's going to be 56 here and 50. Let's go one step further. Let's divide by 2 again, and we'll get 28 and 25. Okay, so all I did was just reduce that fraction there. So now my final function will be a, which is 100, or 100, which is the a, and then our b is 28 over 25 raised to the power of t. Okay? All right, so let's go to the next one. Okay, so you're given this expression log base 3 of 54 minus log base 3 of 2. So we got to go back to our properties of logs. And with the properties of logs, it tells us that when we have a log minus another log, well, we're going to use the quotient property. Okay, so for example, if I had log base 3 of 2 minus log base 3 of 1, that's going to be, using the quotient property, I can rewrite that as log base 3 of 2, the first number, over the second number, 2 over 1, which of course just simplifies to log base 3 of 2 when we do 2 divided by 1. Okay? So let's use that idea to figure out what this one is. So it says given this, again, given this expression, we need to figure out which of these expressions is actually equal to this one. Okay, so we need to figure out what this is actually equal to in order to find that. So we need to find out what number is this expression equal to. So let's simplify it. All right, so we have minus. Let's use a quotient property. So we'll do the first number divided by the second number. And let's simplify that. Well, it's 54 divided by 2 is 27. And I know that log base 3 of 27 is equal to some number. We'll call that number x. So looking at this, remember that a log, the bases are b, this number is our a, and the number out here is our e. And this can be rewritten as b to the e equals a. This is log form, and this is exponential form. So basically we want to rewrite this in exponential form. So this will be 3 to the x equals 27. 3, which is our b, x, which is our e, and 27, which is our a. And you have to say to yourself, okay, what do we have to raise 3 to, what power, in order to equal 27? Well, I know that's 3. Because 3 to the 3 is 27. So now I know this expression is equal to 3. I need to go through each of these logs and figure out which ones are equal to 3 and which one are not. So let's first start with this one on the left. Okay, so it's a minus in the middle, so that means we're going to use our quotient property. So we're going to put the first number over the second number. And let's simplify that. Okay, if that 10,000 divided by 10 is 1,000. And I know this is equal to some number. We'll call it that number x. And remember, if there's no base written here, we always know that it's 10. Okay, if there's nothing written there, it's 10. Now let's write this in exponential form, just like we did before. We'll do the base, which is 10, to the x, which is our e, equals 1,000, which is our a. And then we have to figure out what number do we have to raise 10 to, or what power to equal 1,000. Well, 10 to the 3, or 10 cubed, is equal to 1,000. So that means our x value, or our value for this, is 3. And so yes, it is equal. So we'll circle that one. Okay, so now let's move on to this one. And you're going to use that same idea for all of these. So on this one, you might notice that there's a negative here in the front. Well, we can't use that idea of log base b a equals e and change it to an exponential when there's a negative in the front. So what we need to do is think about our properties. Well, first of all, the negative is not just a negative sign, it's negative 1. And remember, if we had an exponent here to begin with, let's say on the 125, we could take that exponent and move it into the front. That's the power property. But we can also do the opposite. We can go backwards. And I can take that 1, use a different color, and I can bring it back to the spot, to the exponent spot on the 125. So I can go back and forth. So now this is going to be written as log base 1 over 5 of 125 to the negative 1. And now use the same steps we did before. This is equal to some number. We'll call it x. And now it's the base is 1 over 5. We'll raise that to the power of x. And this is equal to 125 to the negative 1. Okay, so now we have, let's see, 5 over here, 125 over here. So we want to think, okay, well maybe I can make the numbers the same base to solve this. Because I recognize there's a 5 here and 125 here, and those are pretty similar. So I can probably change this 125 and make it 5 to something. All right, but again, remember we don't want fractions. So let's first change this 1 over 5. And we know that if I flip this fraction, that the exponent, which is 1 here on the 5, will become negative. Okay, so now, let's figure out, well first let's figure out, okay, 5 to what equals 125? Now I can do this a number of ways. I can just write it down and say, okay, well I know 5 times 5 is 25. And if I multiply another 5, and I can do this, I would have to do this without a calculator. So 5 times 5 is 25. And then times 5. Well, let's use your old multiplication skills here. Bring the 2 up here. Then 5 times 2 is 10, plus 2 is 12, 125. So 5 to the 3 is equal to 125. But don't forget there's an exponent here, negative 1. And then don't forget to multiply your exponents. So negative 1 times x is negative x. And then 3 times negative 1 is negative 3. And now, since our bases are the same, we can just set them equal, the exponents equal to each other. So let's do this. So these exponents now, set them equal. And then let's get rid of that negative by multiplying both sides by negative 1. Or you could divide by negative 1. Either way works. And then x equals 3. And so the answer is yes, this is equal to 3, or equal to the original expression. Okay, so now this one, use the same idea, but now this requires maybe one extra step. So first, if you have 3 logs, focus on just 2 of them at a time. And you could pick either one to either combination. So I could focus on the first 2, or I could focus on the second 2. But just to make, because we all want to be sane, let's start on the left and move to the right. So let's start with the first 2. Okay, so these first 2, log base 6 of 36 plus log base 6 of 6, well, they're separated by a plus, so I can use the product rule, which says that if I have plus, I just multiply my a's. So it'd be 36 times 6. And then we still have minus log base 6 of 1. And then I'm like, no, sorry, I keep saying that. But not on the side here. Let's multiply 36 times 6. Okay, 6 times 6 is 36. Carry the 3. 6 times 3 is 18. Plus 3 is 21. So 216. So 216. Log base 6 of 216 minus log base 6. Okay, log base 6 of 1. And now these 2 logs are separated by a minus, so now let's use the quotient rule. Because remember, if it's minus, we use the quotient rule, which means we take the first number, 216, and set it over the second number, which is 1. But of course, as we all know, if I divide by 1, it's just going to be the same number. So it's equal to log base 6 of 216. And now again, this is equal to some number. We'll call it x. And 6 to the x, let's change it to exponential form, and 6 to the x equals 216. And then I can go here on the side and say, okay, well, I know 6 times 6 is 36. Okay. And then times another 6, well, I know that's 216 because we already figured that out in the first step. So then that means 3 6s. Okay, so 6 to the x equals 6 to the 3, meaning x equals 3. So this one, this last expression also is equivalent to our original expression. Okay? So this next one, we're using this function here, f of x equals log base 3 of x, and we need to figure out, are any of these statements true or are they false? Now this is saying, let's look at A, this is saying that if I plug in 1 over 3 to this function, that it should equal -1. So basically I need to evaluate that and see if it's true. Okay, so let's go ahead and plug in, let's zoom out a little bit so we can see it all. Okay, so I'm going to plug in log base 3 and plug in 1/3, and we're going to do the same thing. I know this is equal to some number, which we'll call x, and then we'll rewrite it as 3 to the x equals 1 over 3. And let's see, well, if I want this to be the same base, but I have a fraction here. But remember, if I flip the fraction, then the exponent just becomes negative. So now it's 3 to the x equals 3 to the -1. And then as you can see, x equals -1 if I wrote out the exponents to the side here. So yes, that one is true. So if I plug in 1/3, it is equal to -1. Okay. So now, I'll do the next one in a different color, so we can keep this all separated. Okay, so now in the next one, we do log base 3 of 81, and that needs to equal 4. So what I can do is I can just actually set this equal to 4, because I need to make sure it's actually equal to that. So now I can do 3 raised to the power of 4 equals 81. So if you're not sure if that's equal, then just go here on the side and multiply 3 times 3, well, I know that's 9, times 3, well, I know that's 27. So then 27 times 3, oh, that's 1, carry the 2, 2 times this is 6, plus 2 is 81. So yes, it is equal. So that one's true as well. Okay, so now on the next one, do this one in green. Okay, so we'll do the log base 3 of 1 over 27, and we want it to equal -3. So now let's again rewrite that in exponential form. 3 to the -3 equals 1 over 27. Well, if we remember, if we have a negative, that's also equal to the same number flipped, and then the exponent becomes the opposite, or in this case becomes positive. So now I'll rewrite this as 1 over 3 to the 3 equals 1 over 27. And I know 3 to the 3 is 27, so this is equal. So that is true. Okay, so now the last one, let's use a different color. Let's do orange. Okay. Now we have 27, so we'll do log base 3 of 27 is equal to -3. And then we'll write in exponential form, 3 to the -3 is equal to 27. I know if this is negative, let's flip it. And you probably already guessed that yes, these are not equivalent, because this is going to be 1 over 27, and this is the whole number of 27, so this does not work. So this last one is false. Okay, so this next problem, all it's asking you to do is write 3 examples of an exponential decay function and 3 examples of an exponential growth function. Okay, so let's first make our decay function. So f of x, sorry about that, f of x equal to some number in parentheses raised to the power of x. So I know if it's a decay that it's going to have to decrease over time. And for decays, our b value would have to be less than 1. So b has to be less than 1. So b has to be less than 1. You can just choose any number or to plug in here. You could choose a decimal, you could choose a fraction, as long as it's less than 1. So one example would be 1 over 3. Another example would be, let's say, f of x equals 1 over 2 raised to the power of x. Another example would be f of x equals 0.08 to the x. Those are all numbers that are less than 1 for our b value. Okay? And then we want 3 examples that are growth. So again, these are all decay. And let's choose a different color for growth. And so for growth, we want our b value to be the opposite, greater than 1. So f of x for the first one, let's just say 2 to the x. Another growth would be 3 to the x. And because we like order and we like things to be the same, let's just go 2, 3, 4, 4 to the x. Those are all different growth examples, just because the number or our b value is greater than 1. Okay, so what you want to do on this is we are going to write the exponential equation in logarithmic form. So we're basically going to convert it. In the second one, we're going to go from logarithmic to exponential form. All right. So first, remember that log base b of a is equal to e. And we can rewrite this as b to the e is equal to a. Okay? So, nice thing about this is that we can go back and forth. So in this first example, we're starting with exponential. So we want to go back to this form up here. Okay, so we know that the b is going to be our base. So that 7 is going to be our base. And then the e is going to be the number on the outside. So let's go ahead and write our a. Our a is going to be 343. And that equals our e, which is 3. And the question only asked me to write it in exponential form, in logarithmic form. So that's all you need to do, It didn't ask you to do any type of evaluating or anything, because if you look at it, it actually already tells you what this log is equal to. So there's nothing you need to do anymore. Okay, so now in this next one, we're going to go the other way. So we're starting with log and now going to exponential. Okay, so we know that our b is going to be our base. And remember, if there's no base written, it is 10. So first write our b, which is 10, and raise that to the e, which is -4. And that's equal to our a, which is 0.0001. And the 1's going to show up anytime now. There it is. All right. Here's your answer. Mr. Osborne is getting frustrated with the computer because it won't work the way I want it. But that's okay. We're going to keep moving on. Finish the race. All right, let's move on to the next one. All right, so now we have to simplify these expressions. Guess what? We're still going to use those properties of log skills that we used back up here to solve these problems. We're going to use those same skills down here. Okay? So now we just need to figure out what are these equal to. And again, this is day one, so no calculators. So first of all, we see a plus. Plus makes us think what? Multiply. So same bases, which is 8, so log base 8. And then we multiply the two numbers using the product property. So I'm going to go ahead and jump to the next step. So 4 times 16, well, that's going to be equal to 64. And now we need to figure out what this is equal to. Well, I say this is equal to some number x. And I can rewrite this in exponential form. 8 to the e, which is our x, equals our a, which is 64. And then we figure out, okay, well, what do I have to raise 8 to get to 64? Well, most of you guys should know it's 2. So x equals 2. Okay, so this next one, you can go ahead and cross this one out because we're going to do a different problem, because you can't use a calculator, and that one would require a calculator. So let's do log base of 2, log base 2 of 16 minus log base 2 of 2. Okay, so now what we want to do is use our quotient rule because we have a minus here in the middle. So log base 2 of 16, remember the first number over the second number, 16 over 2. And we know that 16 divided by 2 is 8. So now let's change that to exponential form. Let's make this equal to some number x, and 2 to the x equals 8. And so we know that if I raise 2 to the power of 3, then I know that sorry for that delay. Computer's having some issues. So then our value is 3. Okay, so this whole expression simplifies to the value of 3. You can write x equals 3, that's fine, or you can say this expression is equal to 3. Either one is fine if you write that. Okay, so let's move on over here to C. Okay, use the same idea. Let's write this in exponential form. And some of you guys are thinking like, oh wait, there's an exponent there. Can't we just move it to the front? But if we move it to the front, then we couldn't put this back in exponential form. So don't be so quick to put that in the front of our expression. You want to do that when we solve equations, which is actually going to be on the second day. Okay, so let's raise this to the power of some number we don't know, x, equals 16 to the 3. So now that we got our numbers written out in exponential form, we want to convert this 16 so that it has the same base as this 2. So we can make them change the number so that they both have a base of 2. So this will be 2 to the 4. And remember, we still have this exponent outside here, this 3. Okay, so then let's multiply our exponents. 2 to the 4 times 3 is 12. So then obviously you can see that x equals 12.
So our value is 12. Okay, so now for this one. This one looks a little different because now we have our log as our exponent, but still use the same idea. Okay? So now, again, this is equal to some value. We don't know what it is. We'll call it x. Remember, this is in exponential form. So this is actually, and since this is in exponential form, which is b to the e equals a, we can rewrite this back in the log form. Log of b equals a, or sorry, log b of a equals e. So let's go ahead and do that. So our b is 6, and our a is x, and then our e is log 6 of 23. Now remember, if I have a log, the same log, or if I have two logs on each side and the bases are the same, these can cancel out. And then our answer is simply x equals 23. Okay, so let's go now to this one. Now this one's just like the other ones. Let's rewrite this into exponential form. This is equal to some number. 8 to the x equals 32. Now let's see. Now we need to make these bases the same. So let's see, 2, if I do 4, no, 4 is too big, so let's do 2. So this is 2 to the 3 times x, or to the raised to the x. And this is 2 to the 5th. Okay, so now we'll do 2 to the 3 times x, which is 3x, and then 2 to the 5th. And then take those exponents, 3x and 5, and let's set them equal. 3x equals 5. Divide both sides by 3. X equals 5 over 3. There we go. Okay, again, let's keep on doing, while we're on a roll, keep on doing it. Okay, so now again, this is equal to some number x. So 4 to the x equals 1 over 256. And we want the same base, so that means we don't want a fraction over here. So let's change that so that it is not a fraction. So we'll flip it, and now the exponent is negative 1. Okay, and now we need to figure out, well, can we raise this to a power where, or change this so that it has the base of 4, or are we going to have to use a different base? Well, let's try it. So 4 times 4 is 16, times 4 I know is 64, and then 64 times 4, well, let's see, that's 16, raise the 1, or carry the 1, 4 times 6 is 24, plus 1 is 25, so that is 256. So that means 1, 2, 3, 4 fours. So 4 to the x is equal to 4 to the 4 raised to the power of negative 1. And let's multiply those exponents. And that becomes negative 4. And so then we know that x and negative 4, set them equal, x equals negative 4. Okay, last one. Don't let the big number scare you. Same steps as before. This is equal to some number x. 4 to the x equals 16,384. And we just need to figure out how many times do we need to raise the power of 4 to get to this number. Okay, so let's go ahead and do the same thing. Now I know the previous problem, that 256 was 4 to the 4th. So let's keep going from there. So 4 times this, that's going to be 4, carry the 2, 4 times 5 is 20 plus 2, well, that's 22, carry the 2, then 4 times 2 is 8. Carry the 2, or plus 2. It's going to be 10, so 1024. Still not there. Times another 4. So 4 times 4 is 16. Carry the 1. 4 times 2 is 8. Carry plus 1 is 9. And then 4 times 0 is 0. And 4 times that is 4. Still not there. So let's do it one more time. And I have a feeling it's going to be just one more because this is 16,000. We have 4,000 here. So let's do 4. Carry the 2. 6 times 4 is 24. And then 4 times 9 is 36. Plus 2 is 38. Carry the 3. And 4 times 0 is 0. Plus 3. And then 4 times 4 is 16. And there we go. So we already started with 4. Then we had to multiply 1, 2, 3 more. So that means we want to do 7 4s. So 4 to the x is equal to 4 to the 7. Hence, x is equal to 7. Okay, so let's go to the next one. So now it says, tell whether the function, this function here, this 1/3 to the raised to the x, shows a growth or decay. And we need to justify that. Now, if some of you guys remember what we talked about before, there is a difference in a growth and decay just by looking at the values in the function itself, and we can figure that out. But here it's asking us to prove that by graphing it, not just by stating, oh, well, I know it's a decay because this b value is less than 1. We actually need to prove it using a table. So it says graph at least 5 points. So let's make 3 columns. Okay, and the first column is going to be our x. The next one's going to be our, actually, us plugging in the value. So f of x. And then the last one will actually be our y value. Okay, so we want to plug in 5 points. So let's make 5 rows. And let's use -2, -1, 0, 1, and 2. You always want to use those values, -2, -1, 0, and 1 and 2. It's usually always proficient enough, or enough to figure out your graph. Okay, so now let's plug that in. So now 1/3 raised to the power of -2. Well, remember that a negative exponent, if we want it to be positive, that basically flips our number. So now instead of being 1/3, we can flip it, and now it becomes 3 squared. So we flip the fraction, and then the exponent becomes positive, and that's equal to 9. Okay, so now plug in the -1 now. And the same idea, flip that fraction, now it becomes a whole number 3, and the exponent becomes 1, so now it's just equal to 3. And now let's plug in 0, and we know that any number raised to the power of 0 is always equal to 1. And then 1/3 raised to the power of 1 is going to be equal to 1/3, because it's basically the number itself. And now 1/3 raised to the power of 2, well, that's going to be 1 squared over 3 squared, and that's going to be equal to 1/9, or 1 over 9. So now let's go ahead and take these points and graph them. Okay, so now let's start with -2 and 9. -2 and 9, so 3, 6, 9. And then -1 and 3. And then 0 and 1. Exponential functions will always have a point at 0 and 1, because 0 is always makes our exponentials equal to 1. Okay, so and then, actually, I apologize, they won't. Most of the time they will. Okay, so then 1 and 1/3. And then 2 and 1/9, so just a little bit closer. Oops, sorry. Okay, now I'm going to make our line, and it starts up here and continues on down here, and it gets really, really close to the line but never really touches. Okay, and there's our sketched graph. Okay, so now we can prove, yes, it's a decay because as it goes to the right, it's getting smaller and smaller and smaller. Okay, now it says identify the approximate x value when f of x equals 6. Okay, so we want to know what is the x value when it's about 6. So remember the x value where it's the f of x is equal to 6 is somewhere about here. Because 6 is along this line. So 1, 2, 3, 4. And so the graph crosses somewhere about close to -2, but I know it's not -2 because we just plugged in that value, so it's got to be less than that. And it's bigger than, less than -1, so somewhere between. So we can take a guess, and I don't know, the x is probably about it's about negative, let's say, I don't know, 1.8 or so. So just kind of a general guess. Just make sure your guess is, less than or is between those two numbers, okay? All right. Okay, so now create a function based on the following transformation from the parent function. So this is our parent function, okay? We're going to start with that. And then we want this translation to go up 7 units. So remember, for us to go vertically translate, we change what we add or subtract to the outside. So for the first one, it's going to be that same function, 3 to the x, plus 7, because we want it to go up 7. And then the next one, we want it to reflect. And reflect, to make a reflection happen, we need to put a negative in front of our function. Okay, so now a horizontal translation. Well, horizontal translation, we change what we plug in. And remember, with an exponential equation or function, we plug in where there's an exponent. So we want to change here what we're actually going to plug in, okay? So for the horizontal translation. So now we're going to go 1 unit right. And remember, x is a liar, so we'll do x minus 1 and then plus 7. Okay, so f of x equals, actually let's rewrite this so that it looks a lot nicer than that. F of x equals -3 to the x minus 1 plus 7. Okay, last problem for day 1. Okay, so now it says identify the graph that represents the function g of x equals 3 to the x. Let's use process of elimination. So first of all, we recognize that the b value is 3. And remember, if the b is greater than 1, it's going to be a growth. So that means our graph should increase. Well, this one's not increasing. This one's not increasing. Those are both decreasing. And then let's start plugging in some values and seeing which it should be. So if I plug in 1, let's say I plugged in 1, this should be equal to 3 to the 1, which is 3. So if I plug in 1, I should get 3. And when I plug in 1 here, I get 2. So it's not this one. If I plug in 1 here, I do get 3. So then this is our graph. Okay, so that is it for day 2. Everything below this is going to be for that is it for day 1. So everything, that's weird. Everything below this line is going to be day 2. Okay, so all this is going to be day 2. All right.